Hi. Today we are going to learn the change of variables in cylindrical polar coordinates. This is the fourth lecture in the third unit. Uh, we already learned so many how to evaluate double and triple integrals and change of order of integration, change of variables, and in change of variables to polar coordinates we learned. Now, in this lecture, we are going to learn how to evaluate a triple integral by changing to the cylindrical polar coordinates. So, first of all, let us know what actually the cylindrical polar coordinates are. After knowing this topic on after knowing about the cylindrical polar coordinates, then we'll learn how to evaluate the triple integral by changing to cylindrical polar coordinates. So, the cylindrical polar coordinates are these are some in three dimensions. To identify a point, we have one Cartesian coordinate system, what we know about three-dimensional geometry and all those things we learned. So in addition to that Cartesian coordinate system, we have another two systems to identify a point related to three dimensions. They are one cylindrical polar coordinates and another one is spherical polar coordinates. In this lecture, we will concentrate only on cylindrical polar coordinates. In the next lecture, we will see the spherical polar coordinates. So the cylindrical polar coordinates are simple extension of the two-dimensional polar coordinates to three dimensions. So in cylindrical polar coordinates is simply the combination of the polar coordinates in the xy plane and the z coordinate of the Cartesian system. All the two put together, we get the cylindrical polar coordinates. Polar coordinates of two dimensions in the xy plane and z coordinate from the Cartesian coordinates. We know how to measure the z coordinate in the Cartesian plane. So uh, to form the cylindrical polar coordinates of a point, take one point in space and take its projection on the xy plane. This is the point P. Take its projection on the xy plane. This is Q. This is the projection of that point P on the xy plane. Now, uh, you have the projection on the xy plane. You know how to identify that point Q on the xy plane in polar coordinate system. In polar coordinate system, as I said, we have the origin and this x-axis as I am taking it, this x-axis, I am taking it as the polar axis. Therefore, this point Q is at a distance of r units and this OQ is making an angle theta with the polar axis. So these are r and theta are the uh, coordinates of this point Q on the xy plane. The point P is at a distance of z units from the xy plane. So this is z. So therefore, this point P is identified with three coordinates called r, theta, and z. R is the distance of the point Q, which is the projection of P on the xy plane from the origin. It is not this distance. Remember, people generally mislead that in cylindrical polar coordinates also, R is the distance of the point from the origin. That is not correct. R is the distance of the point Q, that Q is the projection of P on the xy plane. The distance of Q from origin is R. And this OQ is the radius vector. The angle made by the radius vector with the x-axis is theta, and the distance from P to Q is z. So this is these are the cylindrical polar coordinates. So we know Cartesian coordinate system. We know in Cartesian coordinate system, uh, I think no need to explain to you. Already everyone knows. But anyway, a simple point I'd like to mention here. Suppose this is x-axis, this is y-axis, and this is z-axis. If I take a point, this distance from point P to the xy plane, this is z. This point, this length is your x, and this is your y. Okay, similar this because this is z, this distance is z. Okay, now let us know the relationship between the Cartesian coordinates and the polar coordinates. This is the point P in in Cartesian coordinates it is x, y, z. For the same point in polar coordinate, cylindrical polar coordinates, let r, theta, z be the coordinates. Now this is z, this is r, and this is theta. Now from this q, I will draw a perpendicular on the x-axis as well as the y-axis. So you just here I'd like to mention here this length and this length and this length are same. Therefore, these all the three are y's. This is x, this is x, and all. No, so this is z. This is also z. This is also z. This length is x. This length is also x. This length is also x. This length is also x. Therefore, this length is your y. This length is your x. This is your x and this is your y. This perpendicular distance from a point onto the x-axis, sorry, this is y and this is x. Now, distance of in two dimensions also we know this perpendicular distance from a point on the x-axis y coordinate. Distance on the x-axis is y coordinate. Distance of perpendicular distance from Q onto the y-axis is x coordinate. So this is x, this is also x, this is y, this is also y. Now because this is angle theta, sine theta is here, this is the right angle, this is the hypotenuse. Sine theta is opposites by this, therefore sine theta is y by r, or y is r sine theta. And if I take the cos theta here, adjacent side, that is x by r, x is r cos theta. So these are the z is equal to z. So x is r cos theta, y is r sin theta, z is equal to z. So the conversion from one system to another system is x square plus y square. Here you have so you have x square plus y square is r square, and theta is tan inverse y by x because z is equal to z. So this is conversion from Cartesian to polar. Polar, if you know the Cartesian coordinates, you can find the if you know the Cartesian coordinates, polar coordinates r is root x square plus y square, theta is tan inverse y by x, z is equal to z. But if you know theta and r, x is r cos theta, y is r sin theta, and z is z. So this is about the cylindrical polar coordinates. Okay. Before going to see this animation, if the point is changed, suppose if you take another point, now your perpendicular distance is this, and this is your r, and this is. So if you take several points in space, then this r changes, and this r will change, and you will get something like this. So, and this angle also moves in this way. And this is the plane what we have here. This plane also moves. So these three planes, the three surfaces, this is Z, theta surface, Z surface, and R surface, all the three you can see here in this animation. See here, if you different points are changed, then observe the cylinder, this R value is changing. This is Z plane, this blue one, the red one is theta, R is that green one. If so, that is why if you can observe that a cylinder is coming, this is cylindrical. This is the reason why we are calling that as the cylindrical polar coordinates. The point of intersection of all the three surfaces, so that is this point here. This point is point of intersection of the Z surface, theta surface, and R surface. This is the point of intersection of all the three. If I take this point, this is my Z, this is my R, and this is Z, R, and theta. This is my theta. Okay, so these are the cylindrical polar coordinates. Once you know the cylindrical polar coordinates, easily you can in x is r cos theta, y is r sin theta, z is equal to z. These are the cylindrical polar coordinates. This is from polar to Cartesian. And r is root over x square plus y square. Theta is tan inverse y by x. And z is equal to z. This is Cartesian to polar. That is the relationship. Now let us see the change of variables. Change of variables. Once you have a change of variables, if you have a triple integral in Cartesian coordinate system, if you have a triple integral in Cartesian coordinate system, and if you want to convert that to polar coordinates or any coordinate system, you have this relationship. In place of x, write r cos theta. In place of this y, write r sin theta. In place of this z, write the z only. Dx, dy, dz becomes Jacobian times du, dr, d theta, dz. That Jacobian you have to find out. Jacobian of xyz with respect to r theta z is dou x by dou r. If I differentiate this with respect to cos the r, I will get cos theta. Differentiation of this x with respect to theta is minus r sin theta. There is no z here, therefore dou x by dou z is 0. Similarly, dou y by dou r is sin theta. Dou y by dou theta is r cos theta. Dou z by dou z is 0. And derivative of z with respect to r is 0, with respect to theta is 0, with respect to z is 1. If I expand this determinant, I'll get r cos square theta plus r sin square theta, that is r. So therefore, while converting from Cartesian coordinates to polar coordinates, this dx, dy, dz becomes r times dr, d theta, dz. So this is to be understood. Now, let us see some problems on it. So, just for solving the problems, I'll go back once again and in this cylindrical polar coordinate system, this z is uh, same as the z coordinate from the Cartesian coordinates, and r and theta are the polar coordinates on the xy plane. That means if you have any region in space, to find the limits r and theta and z, what you have to think is take the projection of that entire region on the xy plane. Observe where that projected region on the xy plane falls. Then in that region r and theta varies, and find the z limits as per the given problem. Yeah, here the first one evaluate. So this is one way of the notation. Instead of writing dx, dy, dz, they will write the volume element, that is dv. Dv is all sometimes this is one notation to represent it as dx, dy, dz, where R is the solid cylinder defined by the inequalities. X square plus y square is less than or equal to 4, minus 1 less than or equal to z less than or equal to 2. X square plus y square less than or equal to 4, this is a problem in 3 dimensions. So first problem is this. X square plus y square is less than or equal to 4 if it represents a cylinder. I mentioned many times x square plus y square is equal to 4 is a cylinder. Less than or equal to 4 means the inside part of the cylinder. So in the first problem, what he has given is x square plus y square less than or equal to 4 and minus 1 less than or equal to z less than or equal to 2. Z is equal to 2, z is equal to minus 1. They represent some planes. So x square plus y square is equal to 4. The cylinder extends from a minus infinity to plus infinity, z axis being its axis. So you have here some plane, z is equal to 1 is the plane here. And this is another plane, z is equal to 2. Z is equal to 2. This is z is equal to minus 1. So Z varies from -1 to 2. As I explained in the cylindrical polar, if you want to solve this in the cylindrical polar coordinates, you need to observe that what is the projection of this on the xy plane. Projection in the sense, if I put a light above this from here, if I focus a light on this, so where the uh, shadow of this falls, the shadow automatically falls in this region. So this is your region of integration. So here this part I am writing separately. Yeah, this is the circle. What is this circle? X square plus y square is equal to 4. Why I am calling it a circle? Because the projection is on the xy plane. On the xy plane, on the xy on a plane, x square plus y square is equal to 4 represents a circle. So in this region, r and theta varies. In polar coordinates, what is the equation of this x square plus y square is equal to 4? In polar coordinates, r square is equal to 4 or r is equal to 2. R is equal to 2 is the equation of this. So in this region, to take the polar coordinates, what I have to do is consider, and already in the last lecture, in the lecture 3, I explained the how to take the limits in polar coordinates. Take an radial strip, and this minimum value for r is 0 and maximum value for r is 2, and the theta is this theta varies from 0 to 2 pi. Therefore, for the given problem, this is the one what he has given, triple integral over that region R. I'll change the color, it is triple integral over R. The integrand is x square plus y square plus 2z square dx dy dz. The region is, this is my region from z is equal to -1 to z is equal to 2. This is all my region. This is my region. In this region R, the z, if z varies here, this is the length. So this is the z is -1 here. This is z is equal to 2. So z varies between -1 to 2. And where r and theta varies? R and theta varies here. That I have written here. Therefore, first I will write the limits for z. Z is equal to -1 to 2, and r limits are from 0 to 2, and theta limits are from 0 to 2 pi. And while converting from Cartesian to polar coordinates, I need to substitute in place of x r cos theta, r sin theta, z is z. So x square plus y square becomes r square and 2z square, and dx dy dz becomes r dr d theta dz. But here this order we need to write according to this. Because z I have written here, this first I'll evaluate with respect to z, next with respect to r, and next with respect to theta. So this is integral 0 to 2 pi, integral 0 to 2. I need to integrate with respect to z, therefore r square into r cube is constant. R cube integral for r cube is r cube into z. In place of z, if I substitute the limits, 2 minus minus 1, 2 plus 1, that is 3, plus 2r into z square is there. Integral z square is z cube by 3. Z cube means 2 cube is 8, minus 1 whole cube is minus 1, 8 plus 1, that is 9 by 3 dr d theta. So 3 goes here 3 times. So now I need to integrate with respect to r. So this is 3r cube. R cube integral is r power 4 by 4. If I substitute the limits, that is 2 power 4 by 4 plus 3 into 2, That will be 6 times r. R is r square by 2. R square is 2 square by 2 d theta. 2 here goes 2 times. 2 power 4 is 16. 16 by 4. This goes 4 times. 4 into 3 will be 12. And 6 into 2 will be 12. 12 plus 12, 24. 24 integral 0 to 2 pi d theta. That is theta. That is into 2 pi. So that is 48 pi. So first problem is that. Let us see the second one. Evaluate -1 to 1, minus root 1 minus y square to plus root 1 minus y square, 0 to 4 minus x square minus y square, dx dy dz by converting into cylindrical polar coordinates. Of course, you can do it in Cartesian coordinates, but here he is asking by converting that into cylindrical polar coordinates. So -1 to 1, minus root 1 minus y square to plus root 1 minus y square, 0 to 4 minus x square minus y square. Those are the limits. So for the second problem, -1 to 1, minus root 1 minus y square to plus root 1 minus y square, integral 0 to 4 minus x square minus y square, e power x square plus y square plus z dz dx dy. This is what he is asking us to evaluate. Now, for converting into cylindrical polar coordinates, I need to substitute x is r cos theta, y is r sin theta, and all those things. And for finding the limits, I need to have the region of integration. Let us find the region of integration from the given triple integral. Z is varying from z is equal to 0 to z is equal to 4 minus x square minus y square. So z limits are 0, that is xy plane. Z is equal to 4 minus x square minus y square. What this 4 minus x square minus y square represent? On the xy plane, z value is 0. Z is 0 means it is x square plus y square is equal to 4. So x square plus y square is equal to 4 is a circle on z is equal to 0. If I put z is equal to some constant 1, 2, 3, 4 like that, then if I put z is equal to say 1, then x square plus y square is equal to 3. On the plane z is equal to 1, z is equal to 1. If I substitute, I will get x square plus y square is equal to 3. Again, a circle on this plane, like that. So for different values of z, it represents circles. For z is equal to 4, it represents a point circle. For z is equal to 5, x square plus y square is equal to -1 you will get. Therefore, this, it will not be more than 4. There, from this we can observe that. So this is z. On the z-axis, x and y becomes 0, so only at 4 it touches. This is a inverted paraboloid, like this it will be. So for example, if I take z is equal to say 3, this is z is equal to 3, that means this is a plane. On this plane, you will have one circle. On another plane, you will have another circle. Like that, for different planes, you will get different circles. On this plane, for z is equal to 0, you will have one circle called x square plus y square is equal to 4. This circle is x square plus y square is equal to 4. In polar coordinates, its value is r is equal to 2. Right, and z is equal to 0. And what he has given, x, these are the x limits. X is equal to root 1 minus root 1 minus y square, x square is equal to 1 minus y square, or x square plus y square is equal to 1. So x limits and y limits are varying only in x square plus y square is equal to 1. This is x square y square is equal to 4. X square plus y square is equal to 1 is a cylinder. This is a cylinder. So your region of integration is the paraboloid. Inside it, there is one cylinder. So this is my region of integration. All this part inside the cylinder and this. So here, this is xy plane, this is x-axis, this is y-axis, this is z. And the xy plane here, z value is 0. So where your xy values are varying, x and y values are varying in this circle. What is that circle? Not x square plus y square is equal to 4. It is x square plus y square is equal to 1. Therefore, the circle is r is equal to 1. And here you take one z values varies from, so z varies from here to here. These are the values z, whatever point I take here, minimum value of z is 0, maximum value of z is here. What is the value of z here? Z is equal to 4 minus x square minus y square. X square minus x square minus y square means x square plus y square is minus, if I take common, x square plus y square, that is r square. So z is equal to 4 minus r square for a given r, and r value varies from 0 to 1. Theta values vary from 0 to 2 pi. Therefore, the given integral, triple integral limits are z is equal to 0 to 4 minus r square, and r limits are 0 to 1 and 0 to 2 pi, and integrand he has given as e power x square plus y square is z. This x square plus y square is my r square into e power z. R square plus z I can write as e power r square into e power z. Dx dy dz, as I mentioned, it is r dz dr d theta. It is very easy to now integrate first with respect to 0 to 2 pi, 0 to 1. With respect to z, I need to evaluate integration. E power r square into e power z integral is e power z only. If I substitute the upper limit, e power 4 minus r square minus e power 0 is 1 dr d theta. I'll now simplify this integrand. This is integral 0 to 2 pi, integral 0 to 1. If I multiply those two, this is r into e power 4 minus r e power r square dr d theta. Now I will integrate this. Integral 0 to 2 pi, e power 4 is constant. Integral r is r square by 2. If I substitute the limits, it is 1 by 2 minus, if I multiply this by 2 and divide this by 2, if I take this as t, 2r dr will be dt, e power t dt. Integral e power t is e power t only. That means e power r square. In e power r square, if I substitute the limits, r is equal to 1, e power 1 minus e power 0 is 1 d theta. So if I simplify this, this entire one is a constant, e power 4 minus e plus 1 whole by 2. This can be taken out. Integral 0 to 2 pi d theta. Integral 0 to 2 pi d theta is theta. If I substitute the limits, that is 2 pi. 2 and 2 gets cancelled. This is pi times e power 4 minus e plus 1. This is my integral for that. Let us see the third problem. So evaluate triple integral over r root x square plus y square plus 2 dv is dx dy dz. R he has given like this. Root x square plus y less than or equal to z by 2 less than or equal to 3. So the region is root over x square plus y square less than or equal to z by 2 less than or equal to 3. That means 2 twice root over x square plus y square less than or equal to z less than or equal to 6. So z is in between these two. So what is z is equal to 2 root 1 plus 2 root x square plus y square represent, and what z is equal to 6 represent. You know the values of z is equal to 6 represents a plane. What is z is equal to 2 root x square plus y square represents? On the xy plane, if I take z is equal to 0, again I'll get x square plus y square is 0, which is a point origin. And yes, z, if I take z is equal to some constant, say for example 4 by 2 is 2, root x square plus y square is 2, or x square plus y square is equal to 4. So on the plane z is equal to 4, you are getting another circle. So you are getting several circles whose radius increasing, and you are getting such a curve here. So this is z is equal to, if I put z is equal to 2 or z is equal to 2, if I put, that is x square plus y square, if I, this is z is equal to 2, I'll get one circle x square plus y square is equal to 1. If I put z is equal to 4, then it is x square plus y square is equal to 4 I'll get. So this is another circle. So I need to add all the circles like this. So that is, this is the curve what represent. This is a paraboloid in fact. So this is a paraboloid. And z is equal to 6 is another plane. So this is the plane z is equal to 6. And if I take the projection of this on this plane, so this is the projection what you will get. So projected part is this. That means if I find the light, if I focus the light from the above here, then the shadow will fall here. That is what I can say projection. So this is the projection. Therefore, what is this? This is whatever circle you have that you are adding on the plane. So this is, you are getting this by z is equal to 6. If I put z is equal to 6, 6 is equal to 2 root x square plus y square. 6 by 2 is 3. If I square it, x square plus y square is equal to 9. So this circle is r is equal to 3. X square plus y square is 9. So if I write this part separately, this is r is equal to 3. In this, if I take any r values from 0 to 3, r varies from 0 to 3, and theta varies from 0 to 2 pi. So we know the limits for r and theta. 0 to 3 are the limits for r, theta limits are 0 to 2 pi, whereas z limits are from xy plane here. These are the limits for z. So what is the value of z here? Here z value is 2 root x square plus y square, but in polar coordinates it is 2r, and this is z is equal to 6. Therefore, for this integral, z is equal to 2r to 6, r varies from 0 to 3, and this is 0 to 2 pi. That integrand, what is the integrand he has given? Root x square plus y square plus 2. Root x square plus y square is r plus 2, and dx dy dz is r dz dr d theta. Now just integrate. This is easy. Integral 0 to 2 pi, integral 0 to 3, r into r plus 2, integral dz is z. If I substitute the limits, it is 6 minus 2r to dr d theta. I can take 2 common here. If I take 2 common, this will be 3 minus r. So if I take 2 common, that will come out. Integral 0 to 2 pi, integral 0 to 3, r into, here I have something 3 minus r, 2 already have taken out, r plus 2 into 3 minus r, that is 3r, that is minus r square, and this is minus r square, 3r minus 2r, that is r plus 6 dr d theta. So this is 2 times integral 0 to 2 pi minus r cube. Integral for r cube is r power 4 by 4. For r power 4 is, if I substitute the limits, that is 3 power 4 plus r square. Integral r square is r cube by 3. R cube is 3 cube by 3. It is 27 by 3. Sorry, 3 cube by 3 plus 6r. 6 times r square by 2. R square is 3 square, 9 by 2. 2 goes here 3 times d theta. So if I simplify this first, then I will have 2 times 9 3 is 27. This is another 27. That will be 54. Minus 3 power 4 is 81. 81 by 4. So this is into integral 0 to 2 pi d theta is another 2 pi. So if I multiply this 2 into 2 with 4, you'll have 4, 4, 16, 1, 4, 5 is 20 plus 1, 20 plus 2, 16, minus 81 into pi. Is it right? Let us check once again whether it is. I have a doubt whether it is 2r to 3, not 2r to 6. So if I r times r into r plus 2 to 6r minus 2r, that's right. And this 2 if I take that 2 out, 0 to 2 pi, 0 to 3, if I multiply these two, minus r cube and plus r square, and this is also right, and twice integral 0 to 2 pi r cube r power 4 by 4, r power 4 is 3 power 4 by 4, plus here I have r square is r cube by 3, 3 cube by 3, 27 by 3, plus 6r, r is r square by 2, 3 square 9 by 2, 2 goes 3 times, 3 9s 20, 27, here it is 9, 27 by 3, that is 9, 27 plus 9, 36, this is not 54, this is 36. So 36 into 2 times 4 times, so this will be 4 times 36, 4 6 24, 2, 4 3 is 12, 12 plus 2, that is 144 minus 81 pi, that will be 63 pi. So see the last problem. Triple integral over z by root x square plus y square dz dx dy, where R is the solid region bounded by the plane z is equal to 12 and this paraboloid. So R is the solid region bounded by the plane z is equal to 12 and this paraboloid. Already about this paraboloid here, it is same as this. Z is equal to 2 times x square plus y square minus 6 and z is equal to 12. So here z is equal to 2 times x square plus y square minus 6. If I put x and y 0, then z value is minus 6. And if I give z is equal to some fixed, that means if I put x, y 0, z is equal to minus, on z axis, this surface will cut the z axis at minus 6. And another observation is if I give some z is equal to some value, say 4, and 2 times x plus y square is equal to 10, and x square plus y square is equal to 5. If I give z is equal to 4, I am getting another circle. So, as I said before, with the same explanation, here also it represents a paraboloid. So, this is the paraboloid what I have. This is z is equal to minus 6. So 0, 0, minus 6 is this. And this is z is equal to 12. This is z is equal to 12. When this is z is equal to 12, what could be this circle on this plane? If I put z is equal to 12 here, I will have x square plus y square 12 plus 6, that is 18. 18 by 2 is 9. X square plus y square is equal to 9. If I simply project it on the xy plane, here on the xy plane also I have the same circle, x square plus y square is equal to 9. That means it is r is equal to 3 is the circle. This is r is equal to 3. So the remaining part is very easy to evaluate. Integral. Now z is varying between these two. So the here z value is 2 times x square plus y square is r square minus 6 to 12. And z varies from 0, r varies from 0 to 3, 0 to 2 pi. and root x square, this is z by root x square plus y square, that is r dx dy dz, that is there in the integrand. The integrand, let us see what actually the integrand is. Integrand is z by root x square plus y r square. This is my r, and this dx dy dz is r d theta d r dr dz dr d theta. So r and r gets cancelled. Now integrate it. So because this is a simple integral, already I solved two problems. I am leaving this integral z is z square by 2. So half of z square is 12 square is 144 minus 2r square minus 6 whole square dr d theta. So now simplify this, and ultimately I'm leaving this for you as an exercise. This is one, you will get 1728 pi by 5. This is the answer what you will get. I'm giving this as a homework for you. Just evaluate this integral, square it, a minus b whole square, take 2 common, that 2 square 4 comes out, another 2 comes out, this 2 gets cancelled, expand it, and simple integration. So this is what the answer for the fourth problem. So you have so far what in this lecture what we learned is how to evaluate a triple integral by changing it to cylindrical polar coordinates. So the conversion from cylindrical polar coordinates to Cartesian coordinates and Cartesian to cylindrical coordinates we learned, and uh, for finding the limits in the region in cylindrical polar coordinates, take the projection of that surface or the region on the xy plane. Whatever region you will get in that region, you consider in polar coordinates r and theta, and the z limits will be minimum and maximum values of z in that region what you are considering. So that is how we evaluate the triple integrals, by converting them into cylindrical polar coordinates. In my next lecture, again we will try to evaluate the triple integrals only by change of variables only, but the variables to which we change is spherical polar coordinates. So that we will see in the next